All right. Anybody have any questions from last time? So who remembers, we finished last time talking about something. I said we were going to do a couple example problems this time. Do you remember what that topic was? It's not remembering if you look at your notes. That's reading. Yeah, that's right. What about the stress? Remember what the topic was? I think it's just helpful to sort of jog your memory on this stuff. That's right. That's right. And so it was a topic called principal stresses, and it's a way to find the maximum and minimum tension stress, which is the same thing as saying the maximum tension and the maximum compression. And also then you can use that to find the maximum shear stress. And those are all useful things in figuring out when a material is going to break. Okay, so I'm going to start by doing one example myself, and then I'm going to give you one to work on. Okay, so example. So let's say that in megapascals, you have the stress tensor 12.73, negative 6.270, negative 6.27, negative 2.220, and then 0, 0, 0. By the way, this is a plane stress problem. What plane is relevant here? XY plane, because there's nothing going on the Z face. So we want to figure out first what's the principal stress tensor. And then we want to figure out what's the absolute value of the maximum shear stress. All right, so to find the principal stress tensor, that's that eigenvalue problem. So we're going to subtract our variable. Before I was calling it sigma sub p for principal stress. Often you'll see it written as the Greek letter lambda because that's the symbol for an eigenvalue, and so that's just sort of a general way of doing eigenvalue problems. So we're going to set up this matrix 12.73 minus lambda, negative 6.27, 0. Then negative 6.27, negative 2.22 minus lambda, 0. And then 0, 0, negative lambda. And with this matrix with the sort of absolute value signs on it, that's saying we're calculating this determinant, and we have to set this determinant equal to 0. All right, so I said before that to calculate the determinant of a 3x3 matrix, we'll take this value times this subdeterminant. Then we'll subtract this value times this subdeterminant plus this one. You can do that, but sometimes it's helpful to know that you can also do it along, like you can also do it as this value times its subdeterminant minus this value times its subdeterminant plus this one times its subdeterminant. So it doesn't have to be along that top row. It can be along any of these. It can be along the top row, the bottom row, the first column or the last column? Okay. Okay. So, okay. So we're going to take this 0 times this determinant minus this 0 times, so now cross out this, and it's this times this minus this times this. So you're always crossing out the row and the column that that value is on. And so the benefit of doing that in this case is you have 2 zeros and you only have to calculate one of those subdeterminants. So in this case, I guess I'll write it all out just so you see what I'm doing here. But so we have 0 times negative 6.27 times 0 minus 0 times negative 2.22 minus lambda. And then you have minus the green 0 times its subdeterminant, which is 2.73 minus lambda times 0 minus 0 times negative 6.27. And then the one that matters, negative lambda, so this is, plus this negative lambda times the subdeterminant 2.73 minus lambda times negative 2.22 minus lambda, and then minus negative 6.27 times negative 6.27. What do you get if you multiply those? 6.27 squared. Oh, yes. So I wrote that a couple times. So up here, this is a 12. That doesn't come into the calculation, and this is 12. Thanks. So what's 6.27 squared? 39.3129. 39.31 or 39? 3129. Okay. So I'll just leave it like that. Okay. And so we have negative lambda times, so we're going to multiply this out. What's 12.73 times negative 2.22? Okay, so negative 28.26, and then minus 12.73 lambda plus 2.22 lambda plus lambda squared minus 39.31 is equal to 0. And combine all these and you get negative lambda times lambda squared minus 10.51 lambda, and then minus 67.57 is equal to 0. How many roots are we going to have? Well, you'll always have 3 roots for these eigenvalue problems, but one of these roots is obviously 0 because we've already factored out this 1 lambda. And the other 2, can someone plug that into quadratic formula? Okay. And just the way I set it up, that's round off error, so that's actually 15. Negative 4.5. Okay, so the principal stress tensor then is, well, there's a couple ways you could write it. It could be 0, 15, negative 4.5. Or it could be 15, 0, negative 4.5, or any one of those permutations. Okay. But each one of those principal stresses is one of the diagonal elements of the principal stress tensor. All these are doing is basically we've come up with a stress cube that's like this. Say we have a 15 going this way, a 4.5 going this way, and if we're going to use this first principal stress tensor that I gave, that's saying that the y-axis is parallel to the 15, the z-axis is parallel to the 4.5, and the x-axis just obeys the cross-product relationships you need. And then on the other hand, if we are using this one, then this means that the x-axis is parallel to the 15, the z-axis is parallel to the 4.5, and then the y-axis is whatever you need. Okay. Any questions about that calculation? If you have a TI-89, I think that might be the only TI calculator that does this, but there's a better way to do it. Take this matrix, plug it in as, so in a TI-89, and I'm sure there's a way to do this easily in MATLAB too. Enter this matrix as 12.73, comma, negative 6.27, comma, 0, and then semicolon starts the next row. So I'm just entering that first matrix that I gave you, that first stress tensor. So negative 6.27, negative 2.22, 0, semicolon, then 0, comma, 0, comma, 0. And then put this as the argument for, if you just go to the catalog, the list of functions, go to eigenvalue. I think you spell it E-I-G capital V-L. And it'll just spit those values out. Okay. And I don't think there's really any reason to get used to doing it by hand, although I think there is a reason to understand where the eigenvalue equation comes from, because it sort of makes it clear why eigenvalue equations come up when they do in engineering.
Two questions.
Yep.
First, can you just move up just a little bit?
Yeah.
Thank you. Okay, I see you have a 4.5 on the y-axis. How does that correlate to the?
Well, so let's say that, so all I was saying is you can put any one of those three values anywhere in there. And so so let's do the second one then. Okay. I'm going to write the coordinate system to make this picture correspond to the second one.
Okay, 15 would be x and minus 4.5 would be z. Right?
So then, that's right. And so x would be like that. Z would be this way or the other way. And then Y would have to be this way into the board. No, I did that backwards. Y would have to be coming out of the board, wouldn't it? Okay, and now we need to know what the maximum shear is. So for part B, the maximum shear stress, and that's often written as the Greek letter tau, that's going to be the maximum, so 15, minus the minimum, so that's minus negative 4.5, divided by 2, and you get a value of 9.75 megapascals. There are a lot of materials that are weaker in shear than they are in tension and compression. And so the benefit of knowing the maximum shear stress is sort of clear if you ever see like bone or wood when it compresses, when it fails in compression. Like, let's talk about bone. Like, if you have a car accident where somebody's heel hits the, hits where the pedals are, and you get a compression fracture that way, the way the bone ends up breaking is along a line like this, 45 degrees from the direction of the compression. I don't know what bone I'm drawing there. But this is at 45 degrees. And that is because at an angle offset 45 degrees from that line of compression or tension is the orientation where you get the maximum shear. So even though this fails because of a compression, the actual failure mode is a shear failure. And so if you have materials like this, knowing what the maximum shear stress is that the material can stand is a really important thing. Okay, let me give you another example and you work on this one. So let's say that the stress tensor is 0, 0, 0, 0, negative 1.67, 4.62. That's not possible. Well, let's go 0, 4.62, negative 0.67. And I want you to find the principal stress tensor. Draw the stress cube. And then calculate the maximum shear stress. Okay? And yeah, you can use your calculator. And by the way, like for the exam, for people who don't have this on their calculator, I'm going to always do it as a plane stress thing. So, so one of the variables, one of the roots is always going to be 0, and then you'll just have to solve the quadratic equation. So it won't be too bad to do it by hand. But there's nothing saying that there always has to be 1 0 root. It's just if there is a 0 root, it's easier to do by hand. Anybody want more time? Okay. So what did you get for the principal stresses? Okay. Saw a couple of people agree. So negative 5.58, did you say? 82. Whoops. Okay. And you would get that by calculating the determinant of negative lambda 0, 0, 0, negative 1.67 minus lambda 4.62, 0, 4.62, negative 0.67 minus lambda. So calculate that determinant. You end up with, you're going to end up with only this times this subdeterminant. So you're going to have one root that's equal to 0 because it's already factored out. Then solve this quadratic, and you get these roots. And so the stress cube has one compression, doesn't matter what axis you draw this on, and the compression is 5.82 megapascals. One tension, 3.48. One of them 0. It doesn't matter, no. It just matters that the negative one you put in compression and the positive one you put in tension.
You should be running the opposite arrows too, to show that force tracking on both sides of it.
I guess it doesn't bother me if you don't, because it's really hard to draw the shears. It's easy to draw the normal ones, but later when you're doing shears, it doesn't make much sense. Okay, and so the stress tensor is, you can do it with these different stresses in any one of the diagonal positions, but negative 5.82, 0, 0, 0, 3.48, 0, 0, 0, 0. And then the maximum shear is 3.48 minus negative 5.82 divided by 2. And what do you get for that? 4.85? Okay. Is there any way we could check that? $4.6? That's what you got right there. Okay. Is there any way we can check that answer? Well, there is sort of one way. We know that these shear stresses, that maximum shear stress, like I said, is going to occur on a plane that's oriented 45 degrees between these two. Okay? So if we figure out the traction on a plane inclined like this, we should end up with this as a shear stress. How could we do that? That's right. Yep, figure out that normal. Well, we'll use sine and cosine to figure out the normal vector, and then we'll use that thing where the traction is equal to the stress tensor times the normal. So let's see, what's this? The one I drew here is, okay, so what's a normal vector to this plane? if this is the coordinate system. Well, yeah, let's just first think about that normal vector and then just multiply by the matrix. So I'm just trying to figure out a unit normal pointing like this. So if you start out in the positive x direction, rotate counterclockwise 45 degrees, you're in that direction. So it's just going to be cosine and sine of 45. Okay, so the normal vector is 0.7071, 0.7071, 0. And so then the traction is negative 5.82. That's that principal stress tensor. 0, 3.48, 0, 0, 0, 0, times the normal vector, and you get what I think you did intuitively. Negative 5.82 times 0.7071 plus yeah, so that's going to be, you're right, that's going to be the first component. So negative 4.12. The second component is going to be yeah, 2.46. The third component's going to be 0. And hopefully, let's see. Okay, so now it gets to be sort of a mess actually, because now we have a vector in the other coordinate system. I should never have said this in the first place. You want to see us finish this, or should we just skip it? This isn't really that important. Let's skip it. Do it? Okay. I like that attitude. Okay, so all right, so this is the total traction vector. Now we have to figure out how much of this traction vector is parallel to that normal vector. So we're going to take the dot product of this with the normal vector, right? So basically we have a vector like this. Okay, this is our traction vector. And our normal vector is this way. And we want to subtract off the component of this traction that's parallel to the normal, because what'll be left then is the shear. Okay. So to subtract off the projection, we're going to take 0.7071, 0.70710 dotted with this traction vector. So that's okay, so you get a value of negative 1.17. Okay, and so if we subtract off 1.17, well, subtract negative 1.17 in the direction of that normal, what we should be left with is shear only. So we'll take our original traction, so negative 4.12, positive 2.460, minus negative 1.17 times that normal vector, we're still checking it, yeah. Yeah, this doesn't turn out to be such a great way to do it. Okay, so we get negative 3.29 for the x component. .29 for the y component, 0 for the z component. And now hopefully if we take the magnitude of this, it'll give us 4.65. Did it work? So that's all you have to do to check this. Okay, I would recommend not checking it. Just assume you calculated it right in the first place. All right. Any questions about principal stresses or maximum shears before we go on? All right, so the next thing, we're finally going to get into elasticity. So far, we've just been talking about the definition of stress and relationships between stresses using different coordinate systems. And so to talk about elasticity, I'm first going to talk about the relationship between load and deformation. So that's the relationship between stress and strain. So remember, basically, we want the strain to be equal to a function of the stress. And after we do that, I'm going to give you the requirements for elastic equilibrium. So this is where we're actually solving elastic problems, okay? And this is what finite elements is going to do for us is give us, so what you always want to know with mechanics problems is you apply these loads to an object, what shape does the object become, or what internal loads are developed in the object. I'm going to give you the mathematical requirements. Those don't end up being very useful in most cases because they're hard to solve. And then from that comes finite elements. And this is sort of the end of the mathematical part of this class. Okay, so first is the relationship between load and deformation. We haven't defined any kind of deformation yet, so let's do that first. Just develop. So I'm going to give you what the strain means. If you have an object, so this is it before you apply some loads to it. This is the undeformed shape. And then you apply some loads to it and it deforms into something else. Every material point on the object, so say you're first worried about a point defined by this tiny little box, okay? After the deformation, that little box has moved somewhere. And the vector between where it started and where it moved to, imagine that's pointing to it, is called the displacement. Okay, so you've seen displacement before. I'll call this vector u. So for each point, the displacement vector, sorry, is, it has three components, ux, uy, and uz. And you can define the strain in terms of derivatives, partial derivatives of these displacement vectors. So we'll define the strain at that point as epsilon equal to, so the 1, element is 1/2 times the partial of ux with respect to x plus the partial of ux with respect to x. This could be simplified into just dux dx, but I'm going to write this way because it sort of makes a pattern evident. Then the next element is 1/2 partial of ux with respect to y plus partial of uy with respect to x. The third element is 1/2 times the partial of ux with respect to z plus the partial of uz with respect to x. So do you see the pattern yet? What do you expect to be in this spot? So this, think of this as like the XX element and we had partial of ux with respect to x for both of these. This is the xy element, and this is the partial of x with respect to y plus the partial of y with respect to x. xz has x and z, z and x. Okay, so now we're over here on the yx, and this is going to be 1/2 times the partial of uy with respect to x plus the partial of ux with respect to y. What about the yy element? Yeah, except y's this time, so partial of uy with respect to y. And then yz is 1/2 partial of uy with respect to z plus partial of uz with respect to y. And then the zx is 1/2 times the partial of uz with respect to x plus the partial of ux with respect to z. The zy is partial of uz with respect to y plus the partial of uy with respect to z. And the zz is 1/2 times partial of uz with respect to z plus the partial of uz with respect to z. Okay, so there's the strain matrix. Notice this is also symmetric. Because, so look at the xy position and the yx position. All I did is switch the order of the addition. Okay, so that matches. And so since it's symmetric, there are only 6 independent values, just like there were with the stress. If you define, like if you think of x as being x1, y as being x2, and z as being x3, then you can give all this information using the formula that the ij position of the strain is equal to 1/2 partial of u I with respect to xj plus the partial of uj with respect to xi. So like, look at this zx position. This is saying, so zx, we're saying I is 3 and j is 1, right? So this is du3, or z, dx, plus du1, or x, with respect to the third x, which is z. Okay, so that formula gives you all this information. Let me just give you one more thing here, and then we'll finish this up next time. Elasticity means that the strain is a function of the stress, And in this class, we're not just going to be dealing with elasticity. We're going to have a couple of stronger things we can say about the materials we're looking at. For this class, we also know the materials are linearly elastic. Which means that the strain is equal to some matrix of constants times the stress. And so in order to make it sort of easier to visualize this matrix, we're going to use a new notation for the stress and strain called Voigt notation. Voigt notation for the stress is, so basically the idea of Voigt notation is instead of having a 3x3 matrix with some values redundant because of the symmetry, we're going to represent it as a vector of 6 independent values. We don't lose any information because of the symmetry. So this Voigt notation is sigma xx, sigma yy, sigma zz. So first the 3 normal stresses, and then the 3 shear stresses in the exact opposite order of what you would tend to think of doing yourself. And I don't know why that is, but it starts out with yz, then xz, and then xy. And the Voigt notation for the strain it's the same order, so sigma xx, not sigma, epsilon xx, epsilon yy, epsilon zz, so the normal strains first. And then you have the 3 shear stresses, but we're going to include a factor of 2 on these, so 2 times epsilon yz, 2 times epsilon xz, and 2 times epsilon xy. And those factors of 2 mean that we're talking about engineering shear strain here rather than tensorial shear strain. Okay, any questions about that?
Going with it, I think I missed about 30%. When will I have access to it?
I'll send it to Jake today.
Great.
Okay.
Can you go back one page real quick?
Yeah. Let me stop the